All right. So the agenda of today is actually based on part 2, which is the deep dive. We've previously had a webinar on part 1, going into why transactions, the design goals, the use cases, the syntax, and some code examples. Again, we'll be sending out a follow-up email with a link to the part 1 webinar. But today, we're really focused on part 2, the deep dive. And we're going to be discussing best practices for developers, for DBAs, and some tips and tricks before pushing transactions to prod. All right. So one of the first questions I get when introducing MongoDB multi-document transactions is, why didn't we build these things to begin with? MongoDB was a database for about 10 years before we developed multi-document ACID transactions. And how is it possible for people to build successful applications on MongoDB without them? Well, it really comes down to this point around data modeling. In a relational system, or a legacy tabular relational database, the first rule of data modeling is to normalize your data across tables. And this example here is pretty good. So you might have a customer that has multiple addresses with multiple cities, maybe multiple countries, and you store all of that information normalized across many, many, many tables. Well, in MongoDB, a customer entity might look something more like something on the right, where you have a customer object, and all of those addresses actually live in an array within that object. And maybe you have multiple phone numbers, again, a different array in that object. So that related data is stored together. And in MongoDB, single document ACID transactions have always been there. So as an example, like if I update the field first name here, and then also at the same time, the city, the location of this person, well, that update to a single document in a single statement actually would happen autonomically and give you all of the ACID guarantees you expect. MongoDB has always had these ACID guarantees at the single document level. The novel piece that we're going to be talking about today is extending that guarantee to cross multiple documents, but not only multiple documents, multiple collections within your MongoDB instance, multiple database within your MongoDB instance, and finally, in MongoDB 4.2, multiple shards. So very excited to talk to you about this today. And transactions in MongoDB help simplify development. And what I mean here is application development. So it simplifies the amount of logic you need to keep application side in code. So you don't need to worry about these interim states. So let's say that as a part of my sign-up process in my application, I had to insert 4 documents across 4 collections. Maybe I'm creating a user document at the same time I'm creating accounts document, right? And all of that I need to insert as a part of the sign-up process. Well, either if you're using multi-document transactions to kind of guarantee the automaticity across those collections, across those inserts, you don't have to worry about a partial sign-up for a customer, right? If you're managing that consistency client side, then I would have to have additional logic to account for states in which maybe I successfully inserted the accounts document, but didn't successfully insert the user document required to sign up. Additionally, transactions manage rollback and abort automatically if a single statement fails, so that you, again, don't have to have logic application side that catches an error and then has to go roll back changes across all of the entities. And the third one is point-in-time consistency across reads and writes. So when you open a transaction, it's as if all of those statements happened or were executed at the same exact time in the system, the consistent snapshot view. Shiri will actually be discussing this more later. Now, to go more into detail about some transactions use cases, there are 3 that I like to highlight. We'll go through this very quickly and then get into the technical details in a little bit. First, we have this concept of many-to-many relationships, so positions and trades. In MongoDB, we talk about storing related data together. But sometimes, actually, a common mistake is to try and have an unbounded embedded array within a document. And what I mean by unbounded embedded array is, let's say I have a user document and want to embed all orders, every single order a customer has ever done. Well, if you know my Amazon history, you know that I basically purchase a Amazon order weekly. So I'm adding a document to that array every single week in a way that that document is getting progressively large. And ultimately, one day, it will reach the 16 meg limit in MongoDB. And honestly, documents shouldn't be that big as a sanity check. So when you have this many-to-many relationships, similarly, we have positions and trades. A single position is made up of maybe hundreds of thousands of trades in the finance world. And you don't want to store an unbounded embedded array in a single position document, because that's not a good data model for MongoDB. So instead, when I enter a new trade, I can actually insert a document into a trade collection, and then also at the same time update the position that rolls up the aggregate view of all trades. So that, again, is an example of a way you can use multi-document ACID transactions in order to simplify these complicated use cases. Another one is around event processing. Let's say that I have a customer that's gone delinquent in one of their accounts across my company. Well, I would want to go check and make sure that I find all of their accounts that they have open with me, and then mark that every single one of them is delinquent so that I'm not making incorrect business decisions, right? Once I've marked them delinquent, they're delinquent everywhere. It's not this partial understanding of the customer. So that's an example of event processing. Finally, we have application event logging. So there are, of course, the audit log in MongoDB, where you can kind of audit different types of operations that are happening on the server. But there are also an applications view of privileged actions that actually don't map one-to-one necessarily with types of operations happening on the server. An example here might be change of ownership of a document within a file sharing system. So let's say that I inserted or I uploaded this file, but now I actually want to give someone else ownership of it. I don't want to have ownership of it anymore. The application might log an event like that or want to log that privileged action so that if I then send an email to customer support, that they have a log of this change history and they can actually roll back the ownership if they need to. So that's an example where I might, at the same time as updating the ownership, also insert a log message in my log collection that just creates a history of all of my privileged application logic. So these are three just canonical examples of using transactions to simplify application development. Now, this is a quote that I like to talk about from Cisco. Really, the important piece here is no other database has the power of NoSQL and cross-collection ACID transaction support. Really, you used to have to decide between your scale out and availability features and your transactional consistency features. And MongoDB really has created this world where you don't need to choose at the database or tool level. Now, there might be some trade-offs to have at the operation level, but you can decide at the operation level whether you need to wait for a durable write or an ACID transaction majority commit, or whether you need that operation to actually be always available, even if a majority of nodes can't commit the data. So MongoDB really gives you this tunable model that allows you to make these granular trade-offs at the operation level without having to choose full stop for every application at the tooling or a database level, right? So you get the option to kind of granularly tune based on the operation needs, based on the actions of the application, because frankly, there are always operations within the application that are more important or more critical than others. Now, this road to transactions didn't happen overnight. This has been a major engineering investment ever since the acquisition of WiredTiger. We're actually about 4 years at this point from thinking of developing multi-document transactions in the server, from concept to the development of multi-shard transactions in MongoDB 4.2, which was released earlier this year, I think in August. And it was a fundamental change for the system across the board. So once we acquired WiredTiger, which is MongoDB's default storage engine, we've had to take those transactional guarantees that they've always had at the storage layer and create this coordinated transactional atomicity across multiple nodes. And that's a non-trivial effort, and it took many years and well thought out planning. But this was an area of investment that we wanted to take to make your lives easier. Here are some of the features across many of the major versions that MongoDB has released since we decided to invest in this area. Now getting into some of the developer best practices. The first thing I want to say is that yes, MongoDB transactions are ACID compliant. And yes, even across shards. Starting in MongoDB 4.2, we have the transactional API working in a distributed commit that Sherry is actually going to be discussing later in this talk. Here is what the API looks like, starting in MongoDB 4.2. In MongoDB 4.0, we actually had a more complicated generic API where you would listen for transient transaction errors manually and then retry based on the type of error label you saw. Now we've developed this callback API that retries for you. So here I have two inserts and I'm passing in the session object to each insert. The reason why the session object is bolded is because I actually see this as a common error when I'm looking over the shoulder of people writing transactions. Please remember to pass in that session object to all CRUD commands you hope to execute within the transaction. It's a common mistake. Because here I've started a transaction on session S, I'm not doing the insert on session S, I'm actually passing in the session to the callback API. With transaction is the API here that automatically retries for you. The retrying happens for up to 2 minutes in the system, and that is not configurable today, but we hope to make it a global client-side configurable value in the future. Now you might ask, what is a transient transaction error anyway? Well, the most common error typically in a system like MongoDB is going to be a network error where sometimes packets drop on the floor, right? Either pings get lost, a node is unreachable for some period of time, or there's just at some point going to be a flaky network somewhere. So there's really two things this could mean. Well, either I got a network error on the trip to the server, or I got a network error on the way back from the server. And that's actually a very meaningful difference, because one means, of course, the write was unsuccessful. The other means the write was successful. And you're really left in this undeterministic state. So we introduced an error label where you can actually always get to a deterministic result of whether the transaction committed or not. And that callback API I just introduced takes care of all of that for you. Now, what you'll actually see likely as the most common transient transaction error in your system is probably going to be write conflicts. Write conflicts notify you if the document that you're trying to update in your transaction has been updated since the snapshot time you've been reading it. So you'll get notified if you're seeing a stale version of the data, because again, it goes back to that guarantee transactions provide you, which is a consistent point in time view of the system across all statements within the transaction. Now, here are the fundamental best practices for developers using MongoDB multi-document transactions. The first one is all data modeling rules apply. I know multi-document transactions, or the capability of multi-document transactions, makes it easier to model your data exactly like you would in relational systems, but that's not going to leave you with the best experience with MongoDB. You should still be following MongoDB's data modeling practices so that you get the most efficient workload performance for your system. Second, transactions should not be the most common operation within your application. And honestly, this is a sanity check for rule number 1. So let's say my most common operation is a join across 2 tables. Well, likely that's going to point out to me that I should be storing that data together and not as I would in a legacy tabular database where I would model that data across tables. So 1 and 2 are definitely related. I like to think of 2 as a sanity check for rule number 1. Sometimes there are use cases where transactions may be the most common operation in your application, but really that rule should make you consider whether you are the exception or whether more likely you are the rule. All right, so the third one here is pass the session into all CRUD statements that you want to execute within the transaction. This is going back to that API we just talked about. We bolded the session object that we needed to pass into the inserts. Just remember that you need to do that when you're developing MongoDB transactions. Great. The next one is implement retry logic. Transactions can always abort. We talked a little bit about how write conflicts are going to be common. Network errors are going to be common. And in the face of those errors, transactions will abort. But we want to make sure that if it's a transient error, that we retry from the top. Because if we rerun it again and those errors don't happen, the transaction will be successful. Of course, an example of a non-transient transaction error is like a parsing error where you wrote the query wrong and MongoDB doesn't know how to parse that query. Well, of course, we don't attach that transient transaction error label to those types of errors. So you don't need to worry about that. Now, this is really a rule if you're using the generic API. If you're using our new callback API I just talked about, we actually take care of the retrying for you. Remember, I talked about how we took a lot of the complexity out in MongoDB 4.2. All right, for number 5, don't unnecessarily leave snapshots open. If you are, let's say I have a read-only transaction where I'm reading at a point in time across multiple statements, maybe across multiple collections. I don't want to unnecessarily leave that transaction open. I should be committing and aborting a transaction as soon as I'm done with the transaction. This is so that you can free up resources within the system. The next one is to trigger write conflicts, make sure you're doing writes. I talked about how with snapshot isolation in MongoDB, write conflicts will trigger you. It will trigger if you are trying to write to a scalar version than what you've been reading, scalar version of the document than what you've been reading. So here, what I want to make clear is that reads with snapshot isolation are expected to be stale. You're actually not going to get a write conflict if you're just reading a stale version of the document because, again, we're seeing that consistent point in time. And in order to get notified of more current changes, you need to be writing to the document. The next one is plan for DDL operations. So transactions and the locks at DDL operations will compete for different resources in the system. And you need to make sure that you're planning for DDL operations on namespaces that are happening in active clusters that have multiple transactions against those namespaces. Now, starting in MongoDB 4.2, this gets a lot better where the DDL locks are scoped to the collection that they are impacting. So that's one thing to keep in mind. If you're doing a lot of DDL operations and want to use transactions, you should be likely using MongoDB 4.2. All right, so now I'm going to pass it off to Shiri to go over some operations best practices.
Thanks, Allie. Can everyone hear me?
Yes.
Hopefully you can. Great, super. Thanks, Allie. So yeah, I'm Shiri Cabral, and I am currently a product manager on MongoDB's core databases with Allie, but I was a MySQL DBA for over 15 years. And so I want to kind of talk about, Allie talked about leveraging transactions in the application, and I want to talk about how to operate and support clusters with those transactions in production. So let's walk through some of the things that you should know and the best practices to follow. Now, Allie has already talked about a best practice to not use transactions if you don't need them, and I'm going to go through a few more. So one important thing to remember about MongoDB's transaction is that their isolation level is snapshot. The isolation level determines what data that you expect to see and interact with throughout the duration of your transaction. For example, if your transaction starts at snapshot 102, you're not going to see the writes that happen at 103, 104, 105. You're just going to see the data as it was in snapshot 102. Now, this provides strong consistency because you see a consistent point in time across all of your transaction statements. So even if the data has changed because of a different write or a different transaction, you are going to see that snapshot. Now, the good news is that MongoDB has a built-in way for you to know if the data has changed. For example, let's say you're writing to a document and you have that snapshot 102, and then somebody else writes to a second document, and then you go and try to write to that second document. You're going to get a write conflict. So even though you don't see that that write has happened, you will get a write conflict. So you don't have any worries about overwriting data that is more recent. Now, the important thing to note about this is that the longer your transaction is open and the more writes that come in, the staler that the data that you're going to see is. So if you're making decisions based on snapshot 102 and you're already up to 107, 108, 109, 110, now you're relying on old data. So you don't want your transactions to be open too long because now you're looking at stale data. The other drawback to having a longer transaction is that the snapshots actually store the history, and they store a larger amount of history if you have your transactions open for longer. So this is what the internals of WireTiger looks like. WireTiger is MongoDB's default storage engine, and it's the only storage engine we have that supports transactions. Now, in order to get this snapshot isolation, WireTiger uses this update structure pictured here, which you can see here are keys and values. The structure keeps the changes that have happened across the system since the oldest snapshot. So if there is a transaction using something from snapshot 102, it's not going to get rid of those writes from 103 and 104. If nobody is using anything before that snapshot 102, then it doesn't need to keep snapshots 100, snapshot 101. It doesn't need to keep those. But it will keep those snapshots as long as there's at least one transaction using it. Different transactions can have different snapshot times. So you might start a transaction and then a couple minutes later start another transaction. The first one's still open. They have different snapshot times. The storage engine does try to choose the most current snapshot at the time you start the transaction. Now, the storage engine needs to keep all this history. So the longer you keep your transaction open and the more writes that happen, the longer it needs to keep this. And it keeps it in memory, in a cache. And so we call this cache pressure. As you get more and more data in this cache, you're going to get this cache pressure as you keep transactions open longer and longer. And as soon as you close the last transaction that's using the older snapshot, then MongoDB will evict that from the cache. So you can kind of let go of that cache pressure by not having those open. Transactions will complete by either committing or aborting them. Now, let's say you have a transaction open for an hour. It's a very long time. This means that we have to keep an hour of all of the write history so that WireTiger could still serve reads at that point in time. And it's not just writes on the document that you're using in the transaction, it's writes on everything. Because MongoDB doesn't know in your transaction, let's say you're working on document A, it doesn't know if you're now going to work on document B. It has no idea what you're about to do. So it has to keep those writes on everything. So your entire write volume across all of your data in the database. Now, the update structure is efficient. It only keeps the change of information. So it's not a full document each time. However, if you change your documents by overwriting the whole document, it's actually going to store the whole document. So what you need to do as a best practice is to use $set to set specific fields and instead of doing full document replaces. That's going to keep this cache smaller. You're not going to use as much cache in there, and it means that you can keep transactions open for a little longer. So both the types of writes along with the number of writes is going to contribute to this cache pressure. Now, this isn't quite a best practice. We're going to talk a little bit about features that kind of change the way that you might be using MongoDB transactions or something you might have heard about MongoDB transactions. So in MongoDB 4.0, which is the previous version, the transactions had to be a maximum of 16 megabytes for all the statements that you had in your transaction, start to finish. In MongoDB 4.2, what we've done is every statement in the transaction has to be less than 16 megabytes. So for example, if you had a transaction that had 4 statements and each one was 5 megabytes, you couldn't do that transaction in MongoDB 4.0. In MongoDB 4.2, you can do that no problem. Each statement itself has to be 16 megabytes or less, which usually is an issue because documents in MongoDB have to be 16 megabytes or less. So the good news is that if you wanted that, you have that in 4.2. Now, again, this doesn't mean that now we can have these huge transactions because every statement, you know, we have unlimited statements. We have 100 statements that each have 16 megabytes statements, because WireTiger still has to maintain this history since the snapshot time. And you don't want that cache pressure to build because that will cause your experience to be degraded, right? Things will get a little slower. You'll wonder why transactions are taking so long or even other queries are taking so long. And the good news is that by default, transactions automatically abort after 60 seconds. So if you have your code and you forgot to commit a transaction or abort a transaction, you'll actually get it aborted after 60 seconds if you forgot to close it. You can tune this feature. You can tune it higher. You can tune it lower. 60 seconds is a very long time for a transaction, so I would think really hard before bumping that up. But if you know that you have a particular use that does that, if you're finding a lot of these transactions are aborted because of this, then you could tune that. So again, best practice is to keep this transaction lifetime seconds as small as possible for your values. Now, another feature that we have in 4.2 is mutable shard key values. Before MongoDB 4.2, you are not allowed to change the value of the shard key in your document. So for example, if your shard key was based on city and you were in New York City, you couldn't then update your shard key to say Boston. Now, this doesn't mean that you can just reshard your collection entirely, but this does enable the application to change the shard key field within documents. So I just talked about the global redistribution. If you have sharding based on where somebody is, you can actually move them. Literally, the shard will move to a new the document will move to a new shard by changing this. Another idea is tiered storage, aging out older documents to a low-cost storage shard or a different storage shard. This helps keep the amount of data that you use in your working set smaller. So let's say you're Amazon.com, you go and look at your orders, and you might have noticed that you can get your last 6 months of orders right away. And if you want something older than 6 months, you have to go click on a button. That may be one of the uses of tiered storage, right? You have 6 months of orders in your main database, and then somewhere else you have a different storage. You can do that with this mutable shard key. You could say, okay, this is now an older thing, move it to the older storage. All right, now I wanted to talk a little bit about distributed transactions, which is one of the biggest 4.2 transactions feature. Now what a distributed transaction is it's a cross-shard transaction. So this means you're using sharding and you have a transaction that wants to do writes to more than one shard. So before we start, I want to define 2 important terms. So first, a participant shard. A participant shard is any shard that executes operations on behalf of the given transaction, reads or writes. So for example, if I send a write to one shard and a read to a different shard, both of those shards are participant shards. Now there's also something that we call a coordinator shard, and that's a shard selected, it's definitely a participant, that is responsible for coordinating the distributed commit. Today, the coordinator shard is selected as the first shard to perform writes on behalf of a given transaction, but this may change going forward. So if I send 10 writes to shard 1, and then I send 1 write to shard 2 is going to be the coordinator. So now that we have those terms defined, let's walk through this distributed commit protocol. So what we have here is a query router, also known as the Mongo S, and 2 shards. The query router is responsible for routing those requests to the appropriate shards based on the partition map. Now in MongoDB, the data can move elastically between shards, and that partition map is updated using the shard versioning protocol and the configuration servers. Now this happens seamlessly without any application changes. The details are out of the scope of this talk, but the router is incredibly powerful. Now transactions in sharding must be pinned to the router you use. You can actually have, and we encourage, many query routers, but when you're doing a transaction, you have to do the transaction on one query router. You can't start the transaction on one query router and move it to another. Now this means that if you want to use distributed transactions in 4.2, you also need to upgrade your drivers to 4.2, because by default in previous versions, drivers round robin request to routers so that there's an even workload distribution. Now if the router crashes in the middle of a transaction, the transaction will be aborted. So it is kind of important to make sure that you're pinning to the same transaction, the same query router in a transaction. But of course, if you use the 4.2 drivers, when you start your transaction, it automatically does that pinning for you. Now, in the scenario above, I started a transaction with a 4.2 compatible driver, and my first statement is an insert of document ABC. This insert gets routed to that second shard at the bottom. And now note that the P stands for primary and the S stands for secondary. So of course, it's going to try that write on the primary. And because it's my first write within this transaction, we know that shard 2 becomes the coordinator. So now I'm going to send the second statement in the transaction. Now the second statement in the transaction is an insert, but this time it's a document that has an ID of XYZ instead of ABC. And it gets routed to the other shard, that first shard up there. And you can see that it gets written to the primary on that shard. Now at this point, both of these writes are uncommitted writes, meaning that they're not visible to any other session outside of the transaction that did the uncommitted writes. Both of these shards are participants for this transaction. Now these are the two inserts I want to do in the transaction. I don't need to do anything else. So now I'm going to commit. The application sends the commit message to the router, and that commit gets routed to the coordinator shard. The first thing the coordinator does is send a prepare message to all of the participants, including itself. Once a shard has successfully prepared, the shard has majority committed all the data necessary to commit the transaction. So on this shard 2 at the bottom with ABC, it committed it to the majority of the nodes there, right? So it's the primary and one of the secondaries. A successful prepare is a promise that the shard will be able to commit the transactions. The guarantee of majority commit means that the write is durable to the set within a regardless of failures that happen in the system, that data is not going to be rolled back. That's why it has the majority commit there. Now, because majority commit availability is necessary for these cross-shard transactions are fundamentally incompatible with arbiters because arbiters cannot confirm writes. They have no data. So if you have a sharded system that's using an arbiter in a replica set, we disallow that system. You cannot do a cross-shard transaction on that. Now, once the coordinator has heard back from every participant that the prepare has been successful, or if it reaches a timeout, the coordinator can decide to commit or abort. If there are any failures, the coordinator will abort. And if the coordinator gets all successful prepares, it will decide to send the commit message to all of the participant shards. Now, in the case that the prepares were all successful, which is what we hope, and the coordinator sends the commit message, the coordinator continues sending the commit message to all the participants until it gets successful commit from each one. At commit time, now the transactional changes become visible to outside sessions because we know that it's successful and it's durable and it's what other people should see. Now, at this point, our transaction is complete. Now, this would be a lot if you had to coordinate yourself if you have to do this yourself client side with all the shards and trying to do all this coordination, it's a lot of work. So in MongoDB 4.2, we do this completely for you under the hood. You start your transaction inside a session and it does this work for you. Now, two important things to remember are that you need those drivers to be able to pin the statements to a single router. So you need a 4.2 and higher driver. So the server has to be 4.2 and higher, and the driver has to be 4.2 and higher. and the Mongo S also. So it's the Mongo D, the Mongo S, and the drivers. Cross-shard transactions rely on majority write availability. So of course you need all your nodes up, or at least a majority of nodes up. And if you don't have write availability, you can't do any writes, but you also can't do cross-shard transactions. And because you need this majority write availability, you cannot use arbiters with transaction.
Great.
So I'm going to hand this back to Allie for the next part, and probably could go and answer all the rest of your questions.
Thank you so much, Shiri. Great. So I just wanted to reiterate that ACID transactions were a really huge investment we took on the server engineering team here at MongoDB. And again, this touched every part of our system. And I want you guys all to be aware of cheap imitations in the wild. MongoDB spent a lot of time getting this right and trying to make developers' lives easier, which is core to our mission. Now, if you enjoyed this webinar, we actually have more content that goes in depth even further. So I encourage all of you, if you are planning on using multi-document cross-shard or distributed transactions in the wild, to sign up for this university course called M042, which is a university course about the new features in MongoDB 4.2. I actually teach the sharded transaction section. All right, and then feel free to get started. Just try it out, right? It's one thing to hear us talk about the capabilities. It's another really to try it out and give it a spin. So feel free to not just take our word for it and try transactions yourself in the wild.